So the definition of continuity for any function is basically that a function is continuous at a point if what I get is what I expect. That's my informal definition, which translates very nicely to the formal definition. And I can use that definition for real valued functions, I can use it for vector functions, and I can use it for real valued functions of multiple variables. Okay, so I'm thinking of it informally as what I get is equal to what I expect. But of course we want a more formal definition. What I get, that's just the output of the function. So that would be f at p naught. Okay, that's the point that we're concerned with. Okay, what I expect, well, that's the limit. So that would be the limit as p approaches p naught of f of p. Okay, so the function value is equal to the limit as we approach the point. Same definition we've seen before, just applied to a different type of function. And of course, we say f of p is continuous on its domain if this definition is given for individual points. We would just need that definition to be true at every point in the domain. So if it is continuous at every point in its domain. Okay, and we're going to have a very nifty rule that if I start with continuous functions and then I build other functions out of them using either arithmetic or function composition, then what I build is also going to be continuous on its domain. So what I want to do is just use the formal definition of limit to prove that a particular function, and it's going to sort of stand in for a particular type of function, is actually continuous everywhere. I'm going to take a look at the function f of xy equals x. Okay, so it's the function that takes a point in 2 space and just gives me its x value. Okay, and hopefully you'll believe that the argument that I'm going to use here to show that this function is continuous could be easily modified to show that these other functions are continuous. G of xy equals y, if I spit out the y value instead. Or, I'll just call it f sub 1 of xyz equals x, f sub 2 of xyz equaling y, and f sub 3 of xyz equaling z. So whether I took a function in 2 space or 3 space, if I pick a function that just gives me one of the coordinates of my points, that function is going to be continuous on its domain. Okay, it's essentially the same argument for all 5 of these functions. So I'm just going to show it for this function, and I'm going to choose as p naught, x naught, y naught. Okay, so that represents still an arbitrary point, but for the purposes of our problem, it's going to represent a specific point. I'm not choosing numeric values, so I'm not just showing that this function is continuous, for example, at 1, 2, but for the purposes of our problem, this is representing a fixed but unspecified point. Okay, whereas p, which would be xy, that's representing an honest-to-goodness variable. That function is going to be changing. Okay, so what I'm claiming then is that the limit as xy approaches x naught, y naught, I could also write that as p approaching p naught, but since I've got coordinates, I might as well use them. The limit of the function that just gives me x is, well, what would the function value be at p naught? It would be x naught. That's just f evaluated at x naught, y naught. Okay, so that's what I'm claiming. Now I'm going to just draw a picture. I'm going to actually have 2 pictures. this is the xy plane. And let's just suppose, for the sake of argument, that P naught, which is x naught, y naught, is here. Now, of course, by drawing a picture, I've just made a choice. I put my point in quadrant 1. I'm never going to use the fact that it's in quadrant 1. I'm not going to take advantage of the fact that the x and y that I've drawn here are both positive. I'm not going to be assuming that x naught and y naught are positive. They could be negative. They could be 0. This is just a picture to give me a place to draw some stuff. Okay. And then here's my picture for my outputs. Now, this would be a z-axis, okay? Because essentially, f of xy is always just a fancy name for the z value of my function. So this function is essentially the function z equals x, okay? So I'm drawing a picture for my inputs here and my outputs here, okay? So here we've got our x naught. Notice, you didn't really need to specify, I'm meaning it to represent this one, so I suppose it would be positive, but there's no need for me to draw 0 here. So it really is an arbitrary value here. Okay. Now, our formal definition of limit was that for any epsilon, which establishes a standard for how close we want to get to x naught, we can find ourselves a delta, which is going to be a standard of closeness for how close we want to get to this point here, x naught, y naught. Okay. So that if we control our point and we make it sufficiently close to P naught, then our z value will be within epsilon of x naught. Okay. So I'm going to illustrate that by just saying that gives me this interval. If this distance is epsilon, this would be x naught plus epsilon, and this would be x naught minus epsilon. So we're essentially saying we can force the output of our function to be within that interval. Within that interval, I'm representing it on a z-axis. So bigger than x naught minus epsilon, smaller than x naught plus epsilon. Okay, so what we need to do is figure out how close we need to be here. Well, what I'm going to do is I'm going to just let delta be the same as epsilon. Okay. So I'm going to draw a picture now of all of the points that are within a distance of delta of this point right here. That's basically giving me a disk of radius delta. Everything that's inside of this disk, its distance to the center of the disk, which is my x naught, y naught, is going to be smaller than delta. Okay, so I basically have, I like to call this my disk of closeness. So everything that's within that disk, its distance to P naught is smaller than delta. Okay, if we were in free space, instead of having a disk of closeness, I would have a sphere of closeness. But I would simply choose to let delta be epsilon and calculate a sphere of radius delta centered at P naught, and that would be all of the points whose distance from P naught was smaller than delta. Okay, excellent. So now I can see if I have any point here, any point P, whose values would be x, y, okay, I can now see that this side of the triangle right here would be the distance between P and P naught. But if I draw in the legs of a right triangle, now I'm just going to draw a slightly bigger version of that here. This is the distance between P and P naught. This would be the absolute value of x minus x naught. Okay. Now, as I've drawn it, this point is to the left and below this point. But notice I put the absolute values here. So I could have put the point over here to the right. That doesn't make any difference. I could have put it above. That doesn't make any difference. The only time I wouldn't get a triangle whose hypotenuse was the distance between P and P naught, and one of the legs was this, is if I had the point here, so that it was actually at y naught. But then, the distance between P and P naught would be exactly the same as the absolute value of x minus x naught. Now, I'm drawing a lot of pictures here and considering a lot of cases. That's not actually a full formal proof, but I can write out algebraically. The distance between P and P naught would be the square root of x minus x naught squared plus y minus y naught squared. Okay. Now, if I look at that, that's got to be bigger than or equal to the square root of just x minus x naught squared. Okay. This could be 0, in which case I would get equality. If this is not 0, because it's a square, it's positive, which would make the quantity under this radical bigger, which would make that square root bigger. But this is just the absolute value of x minus x naught, because remember, when we take the square root of something squared, we just get the absolute value of that thing. Okay. So, this algebra here supports the informal arguments I was making with the pictures, okay, that if I choose my delta to be epsilon, if I suppose that I pick a point so that this is bigger than 0, that just says don't pick the point P naught, because for the purposes of taking the limit, I don't care what happens at P naught, I care what happens close to P naught. And this distance is smaller than delta, which is the same as epsilon. Well, if this is smaller than epsilon, this thing, which is smaller than it, will also be smaller than epsilon. Okay. So, if I can make a point in 2 or 3 space be within a certain distance of a fixed point, any of its coordinates are going to be within that distance of the corresponding coordinate of that point. That's all this is saying. Okay. So, that does establish, and I didn't do a formal write-up. I used the formal definition, and I just sort of talked through it. If I were doing a formal write-up, I would have said, suppose this is true, and all of that. Okay. But I just wanted to say that we satisfy that definition, so that this function is continuous on its domain. And I think you can see how we could modify the argument so that if I looked at the function that gave me the y value, if I looked at corresponding functions in 3 space, that we would get continuous functions there. Okay, excellent. That's going to be very helpful, because as we start taking a look at limits, we know from our previous examples that the easiest limits to evaluate are when you have a continuous function and you evaluate the limit by just plugging into the function. So now we've got a tool for seeing certain functions are continuous. In the next video, I'll talk about how functions we can build out of those functions are continuous, and we'll see that a lot of functions are going to end up being continuous on their domain.